Hello, this is Mr. Schmicky. I'm here to try and help you get through the next module in physics since I'm not going to be there today and Thursday and Friday. So let's see if we can go and get through this, and I'll try and do as best I can on this. I wish you were here because a lot of you are good at catching my mistakes, my calculation mistakes. Hopefully I'll keep this new nice and simple. So here we go. We're going to be doing module 10. And this module is all about something called work and energy. And that is like super. I mean, everything I promised you since January, to me, physics is the study of energy in all of its different kinds of forms. Okay? And we've finally reached the point where we've learned enough about mechanical motion and everything else that we can finally talk about mechanical energy. So that's what we're going to do here in Module 10. So first things first, you remember when we went over impulse momentum, we came up by taking a combination of Newton's second law, and we combined that with this first kinematic equation that we did, this one right here. And we combined those two, and we created, we're a good physicist here, we created the impulse momentum theorem. And from that, we discovered impulse and what that was, and from the m times the f, when it spreads into that parentheses in there, the m times f became our momentum. So we were able to discover two new things, impulse and momentum, out of that. Well, we're going to do a very similar thing. And this topic that we're going to do is we're going to take Newton's second law again, F is equal to m times a. But this time we're going to use the third kinematic, which was Vf squared is equal to Vi squared plus 2 times a times the displacement, d. And we're going to combine these. Oh boy, love that square in there, right? Well, it's actually not too bad. Actually, it's going to help us out later on, so watch this. What we're going to do is take Newton's second law, and we're going to put it in place where the acceleration a is in this equation here. So let's go ahead and take Newton's second law, and if we put the m to the other side, divide both sides by m, we're going to have f divided by m is equal to a. So let's go ahead and plug that in right there. So we're going to wind up with Vf squared. If it doesn't bother you too much, I'm going to take this Vi squared right here, and I'm going to move it to the other side. We're going to have to do that eventually, but I was going to save some time. I got a positive Vi squared here, so I'm going to subtract the Vi squared from both sides, and that basically just moves it over here, right? You guys have seen this in algebra enough times. And now over here we've got 2, and then there's that Newton's second law in there, F over m. And then we got times d on the end. Now, just like we did with the impulse momentum theorem, we're going to massage this around for a little bit. So what we're going to do first is we're going to take m and move it to the other side. So we're going to multiply by m on this side and multiply by m on this side. Well, when we do that, we got to multiply both velocities, okay, because there's two terms. So we move the m over there, and now we wind up with m times Vf squared minus Vi squared is equal to 2, and the f is there, and the d is still there. Last thing we're going to do is we're going to get rid of that 2. From this side of the equation, move it over to that side. So we got to divide by 2. Both sides, we got to divide everything by 2. Now the 2's cancel out, leaves us with force times distance over here. That looks really nice and simple. And over on this side, we've created our two new things here. I'm going to bring this as 1/2 of everything over here, right? This is divided by 2, so it's 1/2 of the whole works. So I'm going to move that 1/2 right out here like this, 1/2 m. You got Vf squared minus Vi squared. Now one last step, just like we did with the impulse momentum. Remember when we took our mass and we multiplied it in? We're going to do the same thing with this 1/2 m. So we're going to take 1/2 m times Vf squared. So we have 1/2 m times Vf squared minus, now we take the 1/2 m times the VI squared. 1/2 m VI squared is equal to F times D. And there it is. Believe it or not, that's the monster we wanted to end up with. F times D right here is actually something in physics we call work, mechanical work. Okay, the symbol is just capital W, and all it is force times distance. Wow, nice simple equation. Now as we go along and we go over examples, you're going to realize how important this concept of work actually is. But I don't want to just dump that all on you right now. We'll slowly learn into it. And then these right here, this 1/2 mv squared, that's something, you didn't learn that equation in 5th grade or middle school, probably, but that is something that you did learn about the word for it. 1/2 m times v squared is kinetic energy. Okay, that's kinetic energy. Now I know you learned that in 5th grade science and you heard it multiple times in middle school, so I know it's no new concept to you. And you remember the word kinetic actually means in motion, right? It means in motion. And of course you can see that because it's got a velocity in it right there. So when you look at this whole big huge formula here, we've got two kinetic energies. We've got one here and we've got one here. This one is final because there's a little final on there, and this one's initial. So this one's actually, and we like to symbolize it by just saying KE. We'll put a little I right there for initial. So let me rewrite all this gobbledygook since I messed it up here. We have kinetic energy that's final because it's the final velocity minus the kinetic energy of initial. And that is all equal to work. Wow. And believe it or not, we can reduce this down a little bit more. Remember when we were talking about when you had one position and then you had another position, and when you found the difference between the two, or the change in position or the change in velocity causes acceleration, it was always final minus initial. So we're doing the same thing here. This is actually a change in kinetic energy. So we have just come up with a very serious principle. We're saying here is that work, mechanical work, causes a change in kinetic energy. That, very important. Okay, very, very important. I'm going to put a little clouder on that one, or a star or a highlighter if you got it. Okay, work causes a change in kinetic energy. Now, what exactly do we mean was the cause of the change? How do we know? If you're looking at an object, how do you know if work is being done to it? Well, if we dig back in here where we're deriving all this crazy stuff, we see it right here. It's not the 1/2 is not going to change. The mass of the object's not going to change. You'll notice that the velocity of the object is going to change. It's either going to speed up or it's going to slow down. Why? Because somebody is exerting a net force over a certain distance on that object. Okay? And that's going to cause a change in kinetic energy. Now that is impressively good stuff. So let's go over an example. Okay? We've derived the equation. Now let's see if we can use it. So let's see. We're going to be using kinetic energy is 1/2 mv squared. We're not going to do the initial and final thing. Let's do the basics here. If somebody asks you, what's the kinetic energy of this object moving, we should be able to do that real simple. All right, so our example here we're going to do is, let's say we just take a bowling ball, just a simple little bowling ball. We're going to roll it on a nice flat level floor, no friction. It's just going to move right along. Let's say it's a 5 kilogram. That's like between a 10 and 12 pounder. And let's say that thing is moving along at 10 meters per second. How much kinetic energy does a bowling ball going at 10 meters per second have? Well, that's an easy calculation, right? KE is equal to 1/2 m times v squared. We just plug in those numbers. 1/2 the mass, which is 5 kilograms, times the velocity of this thing, which was cooking along at 10 meters per second. And don't forget, I always forget my little squares. Don't you forget your square. The square is on there. So our kinetic energy is going to be, let's see, 10 times 10. 10 squared is 100. 100 times 5 is 500. Half of 500 is 250. So 250 what? Wow, look at this. Let's see, this will be kilograms. And velocity is meters per second, so that's going to be meters squared over second squared. What an ugly unit. A kilogram meter squared over a second squared. Yuck. So what we did is we came up with a new unit to simplify it, and we named it after Sir Prescott Joule, the guy who came up with the idea of horsepower. And we are going to now call this joules, capital J. Joules, joules, Sir Prescott joules. So we're going to call that 250 joules of energy, kinetic energy. All right, let's take a look at another example. Let's look at the other side of the equation. Work is equal to force times distance. Okay? So let's say we have an object, big old crate of some sort, and we're going to start pulling that thing. There we go. We got somebody pulling that thing, and let's say it has a mass of, what did I put on here? 50 kilograms. Yeah, 50 kilogram object. You're going to exert a 90 Newton force. 90 Newton force on that thing. And you're going to drag that thing a distance, or you're going to exert that force. In other words, this thing's going to be accelerating, right? Since you're inducing a work, it's going to cause that kinetic energy to change, so the velocity is going to change. It's going to accelerate. So as you start pulling this thing with 90 newtons, this thing's going to begin to, let's say there's no friction, it's going to begin to accelerate across the floor. And let's say you exert that force for up to 2 meters. How much work is being done? Well, work's really easy. Work is equal to force times distance. The force you exerted was 90 newtons. Oops, I should have put the units in there, my bad. Times 2 meters. So work is going to be equal to 2 times 90, 180 joules of energy. Real easy. Okay? And again, it's going to be energy as well, because the work causes a change in the energy, and the change is, of course, I think I just blabbered myself to death there. So the work is going to cause a change in energy, so that has to also be in joules of energy. But now this so far has been nice and simple and easy, probably been boring. So let's step things up as we like to do in physics. Let's say we still have our 50 kilogram crate, but instead of pulling it nice and horizontal, no, of course not. Somebody taller comes along, and they're going to pull on it. And yes, I'm sorry, but they're going to pull up at an angle of 20 degrees. But they're still pulling with 90 newtons of force, just like the first person was. But now they're pulling up at a 20-degree angle. And they're still going to move this thing along 2 meters. Now how much work is done? Well, see, do we have to allow for that? Well, actually we do. We got to allow for that angle, because you remember when we were talking about forces before? When we pulled up at an angle like this, what that actually means is that we're pulling horizontally in the x direction, and you're kind of lifting the object a little bit, right? So you're pulling up in the y direction. So if you look at that, which one of these two forces, the force in the y direction or the force in the x direction, do you think is actually making the box move horizontally 2 meters? Yeah, it's going to be the Fx, right? Because you can pull up in the air all the way all day, and the y direction, that's not going to make my 50 kilogram crate move forward 2 meters at all. It's just going to be this component. So if I had to find that component, which we're good at this now, we're working out of this 20-degree angle. This is the adjacent side. That's the hypotenuse. So that's going to be cosine. The cosine of 20 degrees is going to be the adjacent over the hypotenuse. We move that 90 to the other side. And now we can find out what Fx is. Okay? Now, instead of doing this all the time, believe it or not, physicists actually tried to make this a little bit easier on us. Can you believe it? Yeah, not likely. It's going to actually work out for us in the long run, but it's going to make the equation look a little bit meaner. So what we're going to do is they decided to do is to modify this formula. They did still got force times distance, but they're going to put, see that force right there? That's your hypotenuse right there. So if we do this times cosine of whatever the angle is, then it will automatically, all the time, make sure that it's doing the x direction, or the force that's going in the same direction as the motion's going. So on the end of this formula, we're going to add times cosine of whatever the angle is. Okay? So this is our new formula, slightly modified, but very useful. So let's go and try it out. So let's see, work is equal to the force you exerted, which is 90 newtons, times the distance, 2 meters. Now we just put the cosine and the angle, 20 degrees. And it'll automatically take care of all this for us. So we never have to think about that anymore. So let's see, 90 times 2 times cosine of 20 is 169. And again, that'll be joules of energy. Now I want you to look at that. Remember, good physicists, we stand back and we take a look. When we pull straight forward 90 newtons, more energy goes into pulling that thing forward. 180 joules are going to go toward making that crate change its velocity. When you pull up at an angle, you lose a part of that 90 newtons, right? Only part of it, cosine 20 degrees of that 90 newtons is actually going to make it go. So now you only put in 169 joules of energy. That's a little difference in there just because we pulled up at an angle. Okay? Now, let's keep on cooking here. Let's take it, and we're going to go with that same example there. Okay, so we're going to continue with that example. Got to read through my notes here, make sure I present this properly to you and don't confuse you. What if, I'd love to ask that question in physics, right? What if, wish you quit doing that, Mr. Mackey, you always create more problems for us. Well, what if, let's just take a look at that crate. What if that 50 kilogram crate was sitting still on the floor? In other words, just sitting there at 0 meters per second. And then after we pulled on it over a distance of 2 meters, now it's going some new velocity. All right? Now we'll put little motion marks on that thing. It's traveling some new velocity. We don't know what it is. We can actually use our formula to calculate that out. If we go back and we use our original formula, work is equal to 1/2 the mass times VF minus VI. Oop, don't forget the squares, Mr. Maggie. Once again, I almost did. The squares. We should be able to find out what that final velocity is right there. Let's plug it in. Let's see, how much work was done? We decided that it was 169 newtons. And we got 1/2. The mass of our crate is 50 kilograms. The final velocity, I don't know. But the initial velocity we said was from sitting still at rest, so that's 0. So if we solve for VF, don't forget to take the square root at the end there. If we carefully solve for VF, we actually get 2.6 meters per second. So my final velocity over here is going to wind up being 2.6 meters per second. So now we can use that work energy theorem in order to calculate what the final velocity of our box is going to be, which is actually pretty cool. Now I want to do something else just a little bit different off to the side here. So we had no energy over here, right? Because if you look at it, let me do this in a different color since we're considering something slightly different. If we look over here, the kinetic energy of my box when it's just sitting there, of course, the velocity is 0. So 0 squared times mass times 1/2 is just going to give me 0 joules of energy. But how much kinetic energy will I get out over here? 1/2 mv, we'll use the final velocity on this one, squared. Let's see what we get. We have 1/2, the mass is 50, times the velocity we said was 2.6 squared. If you calculate that out, we're going to get 169 joules again. What the heck? Now, rather than get confused, hopefully this will make sense to a lot of you. When you think about it, we come back over here. We said, in fact, if we come way back here, all the way back to the front, what does work do? Work causes a change in kinetic energy, right? Work is going to cause a change in kinetic energy. How much work did it put in? It put in 169 joules of energy. Now think about this. We had an object just sitting on the floor, no energy at all. Now it's got 169 joules of energy. Big question. Where from? Where in the world did you get that energy? The law of conservation of energy states you can't create energy nor destroy energy. Remember that from middle school? So we've got a box sitting here doing squat diddly nothing. It's got no energy at all. And yet suddenly, 2 meters later, it's got 169 joules of kinetic energy cruising along. So where to get that energy from? Most of you probably guessed it. They got it from our person. Right? That person has taken part of their food or their energy in their body and they have transferred it to the box. That is the key magno thing I want you to get out of this. This is like a new, important, ultimate definition of work. You know work causes a change in kinetic energy, right? But what we also can say from all of this, what we've just seen, is not only does it cause a change, it causes a change because work, I'm going to put 3 lines for definition. It's the transfer. Man, underline that puppy right there. It is the transfer of energy. Major, super duper important. Put a cloud, stars, highlighters, whatever, sparkles, stars, glitter, whatever you want, but don't miss that one, okay? Work is the transfer of energy. Now, when you think about transferring energy, you can do 2 ways. You can do like our problem here. We transferred energy into the box, and that shows up as the box going faster. You can look at another example where we can actually take energy away from an object. An example. Well, I know you just want another example, don't you? Okay, here it is. So the other example we're going to go over is, let's say, once again, we've got the wonderful, amazing electric car here. Neat, okay? Let's say it's a 500 kilogram car, and it's cruising along here, initially at 10 meters per second. Down the road here, okay, 20 meters away, there is a stop sign. Okay, there's a stop sign there. I should have drawn that one in red. So, how are you going to get the car to stop? It's got all this kinetic energy over here, right? In fact, it's got, let's go ahead and calculate right here. It's got KE 1/2 MVI squared. It has 1/2 of 500 times 10 squared. If I did that right on my calculator, which I wish I had my students here to help me double check this, but I got 25,000 joules of energy. 25,000 joules of energy. When you get over here to the stop sign, brother, your velocity better be 0, right? You're trying to stop over here, so your velocity's got to be 0. So that means your kinetic energy over here is going to, your final kinetic energy over here is going to be 0. I should probably put an I over here for initial. Forgot about that. Sorry. So where did the energy go? You went from 25,000 to 0. Where'd it go? That's always the question about energy. You can't create it, you can't destroy it, but it can change forms. Okay? It can change forms. And our problem with our person up here, their calories, their food, the chemical energy in their body went into the muscles of their body, which became mechanical energy, and that mechanical energy went into this mechanical energy. Now you got a car going along, mechanical energy of 25,000 joules. We got to get rid of it. How are you going to get rid of it? Well, of course, you slammed on the brakes, right? Right? You slammed on the brakes there. And when you did that, the brakes did work to the car. Okay? So the brakes